All right, good afternoon. So, any question before we start? All right, we are on free vibration for 1 degree of freedom system. So 1 degree of freedom meaning we only have one mass. So we would like to find the response of this system, free vibration, for undamped, because we don't have any damper, 1 degree of freedom system. So if this is mass, if this is the stiffness, we derive the equation of motion for this by applying the Newton method as well as energy method. So x is the coordinates of mass m. So we derive the response of the system, or the answer of this second order differential equation. We ended up to x of t would be x naught cosine of omega nt plus v naught divided by omega sine of omega nt, where omega n is defined as natural angular frequency for this system is going to be s square root of k over n. X naught, what is the value of the x naught? X naught is the coordinates of this mass at time 0, initial condition. And v naught is velocity or x dot of the system at time 0. So suppose you remove this system from equilibrium by the distance of x naught, and v naught at that time is 0. So then release that. So your x naught is the displacement of this system at time 0 would be x naught, and velocity of the system would be 0. So based on this initial condition, the response of the system is going to be this. And omega n is the angular frequency. We can define pendulum oscillation, which is 2 pi divided by omega n, and natural frequency, which is 1 over t, which is omega n over 2 pi. So the response of the system is summation of 2 harmonic motion, 1 sine, 1 cosine. The frequency are the same, omega n. We can add them up and come out with 1 harmonic motion like this, a cosine of omega nt minus phi, where a is going to be s square root of x naught squared plus v naught over omega n squared. This coefficient squared plus this coefficient squared, add them up, square root would be a, and phi would be tangent inverse of v divided by x naught omega n. I have two harmonic function or motion. I come out with one harmonic function. It's easier to deal with one harmonic motion than two. If you like, you can change it to the sine function. It's gonna be a sine function of omega nt plus beta. Beta would be tangent inverse of, just flip this, x naught omega n divided by v naught. So they are the same. I mean, cosine of sine of one angle, it's cosine of pi squared minus theta. So these two are representing the same things. But in this slide, I'm dealing with a cosine function. So if I plot x of t as a function of time, I will get a cosine function like this. It can start at time 0, when you plug in time 0, the cosine of negative phi times a, it's going to be here, a cosine of negative phi would be same as the phi. So it goes up, and the motion is going to repeat itself because it's a harmonic motion. The time between two corresponding similar point, suppose this peak, or these two, or this, two, is gonna be one cycle, so the time would be period of oscillation, which is equals to 2 pi over omega n. At this point, we have the mass at the position of 0. So you have this. At this time, it's going to be at 0. You move it by the x naught and release that. It's going to start oscillating back and forth about this point. So this point is going to be 0. So these are the points that the mass is going to touch that. At the 0 points, we have the maximum velocity, because at 0 point we don't have any deflection on the spring. The entire of the energy of the system is going to be kinematic energy, which is the function of velocity. So since the kinetic energy is at its maximum value, velocity would be at its maximum. So suppose this spring at mass is at relaxed position. If I make 20 centimeter deflection as x naught, time is 0, then I release that. It's gonna start oscillating. I'm gonna click on 1 to show the energy. When this mass is at this position, which is the relaxed position, we don't have any deflection, so the kinetic energy at that point should be maximum. So let me make the time 1/6. So when it comes to that point, the kinetic energy, it's going to be at 0. Now the kinetic energy, it's going to be at the maximum. Then the mass is going to be at this position. And the summation of the energy is going to be the same because we have the conservation of energy. Good? All right, for example, if we have a system with K equals to 10 meter with the mass of 0.1 kilogram, we make x naught equals to 0 at time 0, but at time 0 velocity is -3 meter per second. So this is the initial condition we would like to find the natural frequency of the system and the response of the system. To find the response of the system, I need to find A and phi. A, it's coming from here. A would be a square root of x naught is 0 in this example. V naught is -3 divided by omega n squared. Omega n is a square root of k over n, which is 10 divided by 0.1, a square root of 100, that is 10. Unit would be radian per second. The unit of omega is radian per second, so it's gonna be a square root of -3 divided by 10 squared, it's gonna be 0.3. So A is 0.3 and phi we can find tangent inverse of -3 divided by 0 times not point, 10. Which angle has the tangent value of -infinite? -90. So -3 divided by 0 is going to be tangent inverse of -infinite value. It's going to be good. So if I want to find the response of the system, it's going to be x of t would be A, which is 0.3 cosine of omega into 10t minus 90, it's going to be plus 90. We should plug in by radian, so pi over 2. .3 cosine of 10t plus pi over 2. Cosine of pi over 2 plus an angle is going to be negative sine of pi 10t. So it's going to be, we can write it down as a sine function if you want. Any questions so far? So if I change an equation of motion, we could see that mx double dot plus kx equals to 0. That was the equation of motion for simple mass and spin. So for this one, we could find the angular frequency equals to k over m squared. Now, if I change this variable to y, so say, all right, m y double dot plus k y equals to 0, I just change the variable from x to y. If I ask you what would be the angular frequency for this equation of motion, we still say whatever is the coefficient of y, which is k, divided by whatever is the coefficient of y double dot, which is my in this case. So for the similar equation of motion, we can have we can find the angular frequency same as this equation of motion. Good? Makes sense? Because I'm going to go to the torsional system. On that system, we are going to have theta double dot rather than x double dot, and theta instead of x. So let me talk about torsional vibration, something like the vibration that you may see on the wind turbine. Torsional vibration. Rigid body oscillates what? About the reference axis resulting motion that we call torsional vibration. So suppose there is a shaft which has been fixed to the wall, and at the end of the shaft we have a disc. We have a disc connected to this shaft. So I mean, it's going to be at the relaxed position. So I'm going to twist this disc by the angle of theta naught. So I'm going to twist it by the angle of, so this is the reference. I'm going to twist that. By the angle of theta naught. So I'm going to twist with the shaft, and the shaft is going to be twisted. It's acting like a spring, but torsional spring. Then I release that. This disc is going to start oscillating back and forth about this reference axis. We call this torsional vibration. Everybody can see how it moves. It's a it's about the angle, not displacement. So x has been changed, x naught has been changed to theta naught, and x is gonna change to the theta. So when this disk is at the angle of theta, I would like to derive the equation of motion for this. So second Newton's law says the summation of the torque applied to the rigid body or moment applied to the rigid body would be J times theta double dot. Good? Second Newton's law. So as I said, it's gonna, this shaft with the diameter of D and the length of L is acting as a torsional stiffness that we call it KT. Torsional stiffness. If you remember, for the shaft with the diameter of the D and the length of L, the torsional stiffness is going to be Gj over L. What J is polar moment of area for the shaft, J polar moment of area for the shaft. With the circular cross section, J would be pi d power 4 over 32. And G is the shear modulus. It's a constant depending on the material. And L is the length of the. So this shaft is acting as a spring, but torsional. We have twisted this by the angle of theta. We have twisted this with the angle of theta. So the torque applied from this shaft to the disc is going to be kT times theta, the amount of deflection times the shaft torsional stiffness, like this. How much force this spring is going to apply to this mass, depending on the deflection on the spring, we multiply K by X and find the force applied to the mass. Same thing for the disc. How much the shaft has been twisted, it has been twisted by the angle of theta. So the moments coming from the shaft applied to the disc is going to be negative KT times theta. If I move this to the other side, it's going to Jm theta double dot plus KT theta equals to 0. I talked about KT, but Jm is different than J that you can see over there. the J that you can see over there, it's a polar momentum area for the shaft. This is the mass, polar mass momentum inertia. You don't need to say mass. Polar momentum inertia, because I said inertia, not area. For the disk. Any questions so far? All right, now compare these two. Compare this equation of motion, which was for the mass spring, with this equation of motion, which is for torsional system. If you compare them, they are similar. The variable of x has been changed to theta, so x double dot has been changed to theta double dot. So for this system, the natural frequency, the angular frequency of the system was the square root of whatever is the coefficient of x divided by coefficient of x double dot, which is k over n. Same things here. What would be the angular frequency of this motion? It's going to be kt divided by jm. So you can find the angular frequency, you can find period of oscillation and natural frequency of torsional system. Any question on this? All right, let me solve one example. Again, this J that we used for stiffness of the shaft, it's a term of, it depends on geometry of cross section, which is a circular for the shaft, only geometry. But Jm that you can see on the second Newton's law, it depends on geometry and the mass of this disk. So both criteria would be involved. So there is a auto tire and wheel are assembled to, suspended by a steel rod with diameter of 0.5 centimeter and 2 meter long. So suppose this is the tire and wheel which has been suspended by a steel rod with the diameter of 0.5 centimeter and a length of 2 meter. It's given a displacement and released. So we make a theta naught as a displacement and then we release that. It's gonna start oscillating. So it's gonna start oscillating. Then we start counting the number of cycles or number of oscillation. So it makes 10 oscillation or 10 cycle in 30.2 seconds. So these are the information that we collect by applying the experiment. Is that clear? So we count the number of cycle, 10 cycle, and we count the time. It's going to take 30.2 seconds. So by those information, find the polar momentum inertia of the tire and wheel. So we are looking for Jm. So this experiment or this test that you can see here, it's a empirical things to find or to calculate the polar momentum inertia for a rigid body. So it's difficult to find the polar momentum inertia for a rigid body, but this test or this experiment is gonna help us to find the polar momentum inertia. Let's see how we can do that. So if this is something like this, one torsional stiffness, one inertia, we remove it from relax point and then release that. It's gonna start oscillation. Equation of motion is gonna look like this. For this equation of motion, angular frequency would be this, kt over Jm, and period of oscillation or the time which is needed for one oscillation will be 2 pi over omega n. 2 pi times the square root of Jm over kt. Good? I just 2 pi, did I miss? 2 pi over omega n, 2 pi Jm times k divided by kt. So if I know t, if I know kt, I can solve for Jm. Now let's see what do we have. T, the time to complete one oscillation. The time to complete 10 oscillation is 30.2, so T would be 30.2 divided by 10, which is 0.0302 seconds. So each oscillation takes 0.3. Why we are counting 10 times? Because we just want to minimize the error of counting. So we count it 10 times, then it's going to have less error. So 30.2 divided by 10, kt. Kt is the torsional stiffness. The shaft or the steel rod that we have has this specification. So kt is going to be Gj over L. Gj over L. It's a steel, so shear modulus, it depends on the material. G for a steel, we can read from some engineering references on machine design or mechanics of the material textbook. So G would be 80 times 10 power 9. L is L is 2 meter line, and J is for circular cross section of the steel. It's going to be pi d power 4 divided by 32. Pi d is 0.5 centimeter. I should change it to meter. 0.5 times 10 power negative 2 power 4 divided by 32. G, J, L. If I do the math, I will get 2.45. The unit of KT is torque, which is Newton moment, Newton meter per radian. Newton meter per radian. K for translational is going to be force divided by displacement, Newton per meter. For torsional is going to be Newton meter divided by radian. Now, we are ready to find Jm. 0.302 time would be 2 pi square root of Jm over Kt, which is 2.45. I squared both sides. 0.302 squared divided by 2 pi squared times 2.45. It's going to give me Jm. Jm would be 0.5 67 kilogram meter square. The unit of the J. Yes.
Wouldn't T with 30.2 be
Yes, it should. That point should. There it should. I mean, it's not gonna change. That was my mistake here, but the rest I just copied from. 3 seconds, not 0.3. Thanks for that. So just look at this example as an application to find polar moment of inertia for a rigid body. Suppose you have a rigid body with unknown polar moment of inertia, and you would like to find Jm for that. What you need to do, you need to implement this test or this experiment, have a rod and attach that rigid body to the end of the rod, and you have the physical, the dimension of the rod and the material of the rod, and then just twist the shaft with the rigid body and release that. It's gonna start oscillating. Count the number of, for example, 10 oscillations, and record the time, then find T, find KT, and then you can find Jm. Good? All right. So now let's look at the pendulum problem. We are going to derive the equation of motion for pendulum, and from simple pendulum we are going to move on compound pendulum. So suppose we have a concentrated mass like this, suspended by this rope at this point. So L, L, N. If you remove this by the angle of theta naught and release that, it's gonna start oscillating. It's gonna start oscillating. So we would like to derive the equation of motion for this periodic motion. It's a periodic motion because it's gonna repeat itself regularly. So before I start working on that problem, let me ask you this question. I may have asked this once, but let me ask again. So suppose we have a pendulum like this with the mass of 1 kilogram and the length of 2 meters. There is no friction. We don't have any friction due to the air. So I remove it by 10 degree as a theta naught. Let me make it 20. 20 degree, and then release that. It's gonna start oscillating. So one cycle, if you start from here, it's gonna start from here. When it's back to the same point, you are gonna complete one cycle. So what if I change mass from 1 to 2? And make the same amount of theta naught? What do you expect for period of oscillation, the time? Let's start with the first one, then we can talk about the number. So for example, for this, let me make it more extreme. So by 20, let me have so for this one, it's gonna take 2.85. One cycle is gonna take 2.85. When mass is 0.5 kilogram and length is 2.2 meter. Now I'm going to keep the length the same and mass to 2 kilograms, 4 times. What do you expect for What do you expect for the period of oscillation for T? Say it again. The same, different idea. Let's see. We will get exactly the same period of oscillation, 2.85 seconds. So no matter what would be the weight, we are going to get the same amount of time to complete one whole cycle. So let me back to this question and this problem and derive the equation of motion and see how can we get the natural frequency, angular frequency, and we come out with the same thing that we could see here. So when this is at the angle of theta, I can see the weight, which is mg, is making this moment about the center of rotation. If this is the center of rotation, mg times this distance. This distance is L sine of theta. So L sine of theta. So moment would be for a small angle, if you remember, for a small angle, L theta would be L sine of theta. So I'm assuming that the angles that we are using is the small angle. So summation of the moment would be negative M L theta instead of M L sine of theta. So mg, I forgot. mg L sine of theta, I'm going to use mg L theta. Summation of the moment would be J M theta double dot based on the second Newton's law. Summation of the moment is going to be J polar moment of inertia times the angular acceleration. So if I move this to the other side, I'm going to get Jm theta double dot plus mgl theta equals to 0. Good? So when we have concentrated mass at the distance of L, Jm for a concentrated mass located at the distance of L from center of rotation is going to be m L squared. So for this, I'm replacing Jm by this. M L squared plus m L and GL theta equals to 0. I have 2m, I can cancel them out. 1L here can be cancelled out by this. So I'm going to get L theta double dot plus G theta equals to 0. So this is going to be the equation of motion for the system. So the pendulum has this equation of motion, like this, mx double dot kx. The angular frequency of the system is a square root of whatever is the coefficient of x divided by whatever is the coefficient of x delta. So they are the same except theta, x has been changed to the theta. So omega n would be s square root of g gravity divided by L, length of pendulum. So if we have a pendulum with the length of 0.5 and mass of 1 kilogram, the omega n for this should be g divided by L, which is 0.5, or 2g, s square root of 2g. So if I what did I use? So the periodic oscillation is going to be 1.429, which is 2 pi over omega n, which is s square root of 2g. If we do the math, we should get the same thing that we got here. So if I change the length to 2 from 0.5 2.85, which is twice greater than this, because 2 is the same for this. L is going to change to 4, g divided by 4 is going to be g divided by 4. So 2g versus g divided by 2. Which is 2 times greater than this. So 2 times this is going to be 2.85 seconds. Now, if you go to the other planet, yes. If you go to the moon, let's start with the moon. Gravity is going to be different. So g is going to be less. So 2.85 is going to change to 6.92 second. And if you go to Jupiter, it's going to take 1.75. By this experiment, if you are in an unknown planet, you can find the gravity on that planet. Just try. T would be 2 pi divided by omega n, which is 2 pi times square root of L over G. So if you know T, if you know the L, you can find the gravity on that planet X. So if on planet X, T is 2.375, you can find the gravity of that planet. And in no gravity, what's gonna happen? It's not gonna rotate, exactly. It's not. If you move it, G is 0. If I release that, G is 0, there is no moment to make the rotation. All right. Any question before we move on? Compound pendulum. Now, that was a simple problem because we had concentrated mass oscillating about 1 point. Now, what if I have a rigid body which can be rotated about a rotational point? So, how can we derive the equation of motion for compound pendulum problem? So, from simple pendulum, we move on. Let me work on this. I derive the equation of motion by using the Newton's law, second Newton's law. If we assume that we have conservation, we don't lose any energy, the summation of potential and energy would be constant. We can use this equation. Potential energy plus kinetic energy is constant. So if you differentiate both sides with respect to time, we should get the equation of motion. So to do that, we should find the potential energy and kinetic energy of the system when this is at the angle of theta. So when this is at the angle of theta, the angular velocity would be theta dot. The velocity would be r, which is L, times omega, which is L theta dot. And the kinetic energy would be half of m v squared, half of m L theta dot squared. Potential energy, if this is the reference point, depending on how far you have moved the mass from the reference point, you have absorbed some potential energy on the system. This guy is L minus L cosine of theta. This is the this part is L cosine of theta. If you subtract from L, you will get this height. So L minus L cosine of theta, mg times that is gonna be the potential energy. Good? You are gonna use this method again and again on the homework problem, and maybe on the exams problem. So kinetic energy plus potential energy would be half of m L mv squared. It should be both L squared theta dot squared plus half of, not half, mg L minus L cosine. Everybody can see how we get potential energy. mg times that distance, which is L minus L. Now differentiate this with respect to time. So half m L square are constant, half m L square are constant. This is changing with time. So 2 theta dot times derivative of theta dot with respect to time plus mgl is constant, derivative of mgl is going to be 0, so I should differentiate mgl cosine of theta with negative. mgl is constant, derivative of cosine of theta would be negative sine of theta times this is going to be positive sine of theta, so I'm getting mgl sine of theta, derivative of theta with respect to time. And this must be equals to 0. Derivative of kinetic energy plus potential energy must be 0. This half can be cancelled out by these two. M can be cancelled out from both sides. L can be cancelled out with this one. Derivative of theta with respect to time is going to be theta dot, can be cancelled out with this theta dot. So I'm getting L, derivative of theta dot with respect to time is going to be L theta double dot. L theta double dot. Plus, here I'm getting G sine of theta. For a small angle, sine of theta equals to theta, I'm getting G theta equals to 0. So the energy method also should give us the same equation of motion if there is no loss of it. Make sense? So any question on this? Alright, now let's move on. Compound pendulum. In single pendulum we had just concentrated mass attached to the rope and we had rotation, oscillation. But what if you have a rigid body which can be attached at any point O for example, and it's gonna start oscillation about that axis of rotation. So we call it compound pendulum. It's a pendulum, it's not simple because it's a rigid body, but it can rotate about the axis of rotation which is passing through the point O. We would like to find the equation of motion for if point G is center of gravity, I connect this to the center of rotation. When center of gravity is at the angle of theta, with this axis, we would like to find equation of motion for this oscillation. So the mass of rigid body, which is mg, is applied at the center of gravity. So this force, same as simple pendulum. This force times this distance is making rotation. What is this distance? Is d. D is the distance from center of rotation to center of gravity, times sine of theta. D sine of theta will be this distance. So summation of the moment negative mg d sine of theta. So summation of the moment based on the second Newton's law would be J with respect to center of rotation O it's important which axis we are talking about. So it's about the center of rotation. It's the axis of center of rotation, not center of gravity. Jo theta double dot, it's going to be negative mg d sine of theta. So if I move this to the other side, I will get J naught theta double dot plus mg d sine of theta equals to 0. Sine of theta for a small angle is going to be theta. I will get J naught theta double dot plus mg d theta equals to 0. So as you see, it's different than simple pendulum. We are gonna work on this equation, define some other terms like radius of gyration, and then we simplify this to define more terms like center of percussion, and then we finish this topic on next week. So I'm gonna collect the homework too, I guess. And I'm gonna post the new homework by tomorrow. No, I just
Thank you.
Thank you. Goes for overload registration.
Just for the theater, someone doing theater. Like, you know, classes, like, not the classes, like, they're gonna be doing, like, a soundboard for, like, the theater, plays and stuff like that.
You want to add it?
Yeah,
Can you add it now?
yeah, like, yeah.
It's a theater too.
Yeah, it's just like it's like a thing I'm doing. It's like a weekly thing I'm doing just for a week.
Okay.
So it's like
Is the B block or is just a regular?
it's just a regular.
Okay.